Okay, great. Well, I'll go ahead and do an introduction here. So welcome everybody to the seminar here. I'm very happy to introduce Ali Mehrizi-Sani. He's a professor at Virginia Tech. And today he's going to be discussing some ideas on control of low inertia microgrids and inverter-based resources. So I think we'll see a nice combination of some control systems and power electronics. Okay, so just a real quick bio about Ali. So he obtained his PhD from the University of Toronto in 2011. He's currently an associate professor at Virginia Tech. His areas of interest are in power system applications of power electronics and integration of renewables. He's an editor of IEEE transactions on energy conversion and power engineering letters, energies, and MDPI electronics. He was also an editor of IEEE transactions on power systems, power delivery, and Wiley International transactions on electrical energy systems. And he was a chair of a task force, and he was a recipient of the 2018 IEEE Power and Energy Systems Outstanding Young Engineer Award, as well as a variety of other awards. So Ali, please take it away.
Sure. Thank you, Brian, for the introduction, and certainly thank you for the for invitation having me. Just double check. Can you see this screen, the slides?
Yes.
Okay, perfect. Well, thank you, and thanks to everybody for being here. It's so I actually was in the state of Washington, and of course on the other side of the Cascades for about, I guess, 7 years. So it's good to be virtually back. I still call Washington home. So it's very nice to be doing this talk again. Thanks. So I'll be talking about ideas for control of low inertia microgrids with inverter-based resources. And of course, this work is based on what my students have been doing over years. And some of the results are also based on the collaborations we have had with other universities. Toward the end of these slides, I talk about those collaborations, and then also have essentially a list of publications coming out of our work in this regard. So since I will be discussing our work in terms of microgrid operations, let's define what a microgrid is. And the definition that I have here on the screen is probably the most commonly used definition based on what the Department of Energy uses. So essentially, microgrids are complete but miniature, essentially they are micro, power systems that are an aggregate of co-located resources. Essentially, they are with the same kind of geographical vicinity. Those resources can be loads, can be generation units, can be storage units, which we collectively call DERs, distributed energy resources. And then the microgrid can be interfaced to the main grid at the distribution level through a point of common coupling. We used to actually have only a single point of common coupling, but kind of newer variations, newer thoughts of microgrids actually promote multiple PCCs. And of course, key is microgrid can operate as in a grid connected mode. So essentially supplementing what the grid does, or in the islanded mode when, for whatever reason, the microgrid needs to disconnect from the grid. For example, when the quality of the upstream grid is low, or for other reasons. So it should be able to operate in islanded mode as well. And of course, the transition between these two modes. Actually, that idea of the transition at some point, maybe about 10 years ago, was such a big thing that was a huge kind of a research area, how to make sure microgrid can sustain itself during the significant disturbance that it goes through when it moves from grid connected mode to the islanded mode. Of course, microgrids have lots of applications. Many of these applications are quite niche applications. For example, microgrids in remote areas. One good example is actually remote communities here in Canada. Well, I'm physically in Canada today. In Canada, essentially northern Canada, which is practically the northern pole. It's not really economical to have power lines drawn from all the generation centers up to those communities. Communities are typically very small and these large distances. And then the cost of electricity in those communities are quite high, something in the order of $2 to $3 per kilowatt hour, and compare that to 8 to 10 cents that you get in bigger cities in the Northwest. So that's it's significant application of microgrids. In fact, one of the Canadian national labs, NRCan, they have been working on microgrids essentially for this kind of the federal type of mandate for some time. Another application for resiliency to help, of course, with sensitive loads in buildings and campuses. And another application, kind of a newer application, but something that's finding traction for DC loads. Essentially, well, the idea is if my loads are going to be DC, then I can save on DC to AC conversion process by essentially having the system, in this case will be the microgrid, to be DC as well. There are lots of data servers. Actually, Washington has lots of data servers. My new state, Virginia, we also have quite a lot of data centers in Northern Virginia. So those can be efficiently implemented as microgrids. Of course, many of our office loads, computers, chargers, and so on are also DC. Here's an example of a microgrid. This is the former Navy Yard in Philadelphia that has been converted to a commercial industrial zone. This was a project we did with funding from the DOE. Our collaborators were Awesome Grid at the time, PNNL, UC Berkeley, the City of Philadelphia, and so on. And the idea was to enable operation of this Navy Yard as a microgrid to ensure that we had availability of power for the kind of the highest tech the tenants that they had. The bakeries, essentially commercial entities, bakeries, Old Navy, the clothing store, offices, and so on. So that was kind of a demonstration project quite a few years ago. And so at the same time, we're also looking at the operation of the power system with large shares of inverters. Well, why is that interest in inverters? Where is that interest in inverters coming from? Well, this is a map of the US. There are many states that we can see that have renewable portfolio standards. Washington, in fact, actually Washington, my previous state and my new state, both of them have quite aggressive renewable portfolio standards. Both of them 100% by 2020, 45. California, 100% similar by 2045, and so on. So just a disclaimer that most states in the US do consider hydropower to be part of the renewable portfolio. Washington actually considers, I found this back when I was just became a professor, that Washington actually considers fuel cells. It's based on hydrogen, but they also consider that to be part of the renewable portfolio. Essentially, that means they can use some of the incentives. So now, with the exception of the hydropower, most other renewables, mainly PV, solar photovoltaics, and type 3 and type 4 wind units, they use inverters to interface the energy generated to the grid. Essentially, in the PV units need inverters to convert DC power to AC. Wind units already generate AC, but then they need inverters to be able to condition that power and interface it to the grid at a higher quality, essentially nicer sinusoidal regulated frequency type of waveform. Now, we know more or less how to operate a grid with some inverters, but when the share of inverters increases, then many traditional concepts are going to be challenged. So we're going to be talking about those. This is actually another graph showing the electricity generation trend in the US. When I was a PhD student, I remember coal was about 70%. That, of course, has gone down to about 20%. You see renewable energy has been on the rise steadily over the last 2 decades. We also have natural gas on the rise. It's, of course, a fossil fuel-based generation, but it's not too unclean. So they have kind of this favorable position compared to many other generation points. So with this shift to inverters comes variability, more distributed generation, different protection strategies, different power flow patterns, and so on. Essentially, what's happening is the generation and load mix is changing. So for example, the BPA service area, BPA, I'm sure you're familiar with Bonneville Power Administration, providing power to Washington, Oregon, Idaho, part of Montana. They have experienced several times 100% wind generation. Typically, this actually happens in fall, typically in October timeframe, because there is not a lot of water. There is fish restrictions, and most of the generation actually can come from wind. The ERCOT system in Texas has also had instances of 50% instantaneous wind. And Australia, the power system have also experiences quite routinely more than 70% instantaneous inverter-based generation. So again, we are moving from a single generation-based power system to a power system that has more and more inverters. If it's the main power system, as we discussed, because of wind and PV and so on, we're getting more inverter-based generation. If it's microgrids, many of them do use inverters as their main form of interface for between generators and the system. Of course, a similar thing is also happening for the loads. We are moving from just motors to drives, which are really motors plus inverters that we can allow more control. Loads are also in terms of lights, more and more lights are becoming converter-based, and modern appliances also have intrinsic converters inside. So on both generation side and load side, we are moving to the more and more inverters. So this transition has also brought about changes in the operational standards. For example, the minimum standard for integration of renewables, IEEE 1547, in its first iteration, it actually required that inverter resources, or DRs in general, would disconnect in response to a disturbance. So essentially the idea was, hey, we don't really know, and this is 2003, we don't really know how you work. So when something happens in the system, please just disconnect, hoping that you're not doing too much harm. It took the community about 12 years to come up, kind of to feel the need and then come up with an updated version of 1547. So 2015, the standard was updated to actually require the DER units to write through disturbances. So from, hey, disconnect, now the inverters or DERs again in general are required to write through. So the idea is, well, don't disconnect, we need your generation, but don't do much else either, because we still don't really believe in your capabilities, right? That was kind of the thinking. And then only 3 years after that, 2018, the standard actually started to requiring the DR resources to provide support. So previously it was a 2003 disconnect, then standby, then actually actively contribute. That's the 2018 version. And that's what the new power system terminology generally refers to as grid forming capabilities. Things like voltage right through, frequency right through, voltage support, frequency support, startup ramp rates, and so on. Then these inverters that we talk about, regardless of their topology, regardless of exactly how their circuit looks like, they can operate in two main modes of operation, either grid following or grid forming. Grid forming has become kind of a buzzword these days. Essentially, they're considered to be the key to operate the power system with large shares of inverter-based resources. And the terms are slowly becoming a standard. I remember I first read these terms in a paper. It was a very good paper back in 2007. But I guess the power system community at some point decided that it needed to refer to power electronics with terms that were familiar for the power system community. So they introduced the term grid in kind of the classification of these inverters. So now that we call them grid forming, grid following, and so on. Of course, names are important. The moment the term grid forming became common use, power electronics also became a friendly thing. So that has helped quite a bit with with using more and more power electronics in the power system. Now, the way that I try to actually understand these terms is I kind of say grid here almost means voltage. So a grid forming would be an inverter that creates or forms the voltage and for the grid, and then the grid following would be the one that would follow the voltage of the grid. And roughly these terms are equivalent to slave and master controllers in microgrid terminology, or again, roughly PQ and PV buses in the standard power flow problem. If we want to go further down, sometimes we further divide grid following inverters into grid parallel and grid supporting inverters. So grid parallel ones are the inverters that their output is agnostic to the grid conditions. So essentially, say a non-dispatchable PV unit based on maximum power point tracking. So they just do what they want without really regards to what's happening in the power system. And then something a little bit more smart, something that has some brain, is grid supporting units that they are dispatchable. They do respond to the grid commands, for example, by changing their real power. And for example, they can participate in power sharing. So, so with that introduction, let's see what we would specifically be talking about today. So we're going to look at the problem of control of gray boxed and variable systems, variable inverter systems. I say gray box because instead of black box, because typically we know some stuff about our inverters. We don't know all the details, but it's not that we are totally in the dark either. Now, what is the challenge? So inverters, the models are not always available to us. Manufacturers, vendors do not share full-fledged models all the time. Inverters, of course, they're based on power electronics, so they're more sensitive to abnormal operations compared to traditional, good, robust synchronous generators that we used to have in our power systems. And so I just mentioned we don't always have their models, but we don't always have full control over the parameters of the controllers either. So again, we know some stuff about those inverters, and we have some control, but not a lot of control. And at the same time, another reason that control of inverters is a challenge is because of the setting that we use them for. So we just mentioned that we use inverters mainly when we have lots of inverters or when we have microgrids. And both cases, the system changes quite frequently. So redesigning controllers would become problematic, would become quite a bit of a challenge. And then even if you do redesign, then the new controller would work only for some pre-specified configuration, and the performance again deteriorates when the whole system changes. So here's an example of what I mean by this. Here on the top right, you see the original system and its response to a certain step change. The overshoot 15%, settling time 32 milliseconds, something acceptable, not ideal, not too beautiful, but it works. Now, same system, I disconnected one of the loads. Of course, this was a microgrid system. I disconnected one of the loads and I applied the same step change. Now, the overshoot is almost twice bigger than what I had before. So from 15, I went to 26%. And my settling time is also longer. Instead of 32, now I have 67. So same system, same disturbance, well, almost same system without the load. Same disturbance, now I get very different responses. My system has become quite a bit smaller. So the main question is, how can we make sure our inverter units are tightly controlled and do not violate their limits, even when the host grid or microgrid changes significantly? So that's kind of the control problem we are going to be talking about today. Of course, control is not new. There are lots of efforts in terms of control. It's been an active area of research for as long as I remember, and it will remain an active area of research. Essentially, any engineering system you build, you have to be able to control it. Otherwise, it will be kind of like drunk driving. So that is going to be a kind of an integral part of whatever we do as engineers. If I want to very kind of roughly kind of categorize existing approaches for control to ensure that the dynamics of the systems are handled, we have analytical formulation and model-based tuning, in which essentially we develop a mathematical model of the system and then use linear, nonlinear control methods to devise the control parameters, or optimization kind of based methods where we create a model of the system in a transient simulation program. PSCAD is very commonly used these days, and then we run multiple cases to minimize some cost function by finding the optimal values for those control parameters. This method can also refer to machine learning based control design, because essentially at the end of the day you have to optimize the gains for your neural network or whatever type of kind of design you have. But the problem is they have robustness with respect to topology. Essentially, when the system changes, we have to redesign these controllers. And if retuning is needed, then it would be difficult because we have to go back to the field and implement the new changes. Of course, they need the models of the system, which is not really a luxury we can always afford in terms of inverters. So we're going to look at this from kind of a fresh perspective. So essentially kind of an alternate idea. Instead of updating the controller structure and the parameters, which is essentially what the bulk of literature does, we seek to get a better response by instead manipulating the set point itself. So when you want to design a better controller, of course, the first thing that comes in mind is to update the controller itself. But in my case, if I do not really have access to that controller, then the idea is I try to manipulate the set point instead, which is essentially the easiest thing I can change because set point is something I provide anyways. So, but how? So we don't want to change our original controllers, as I said. We want to keep them in place, but we want to augment them with an add-on feature. And essentially, the basics of how this method works is this small kind of graph over here. So assume the set point for some x of t has changed from x1 to x2. And that x of t could be any variable that I control. Could be current, voltage, real power, reactive power, angle, torque, whatever I'm trying to control. So the set point changes from x1 to x2. And if I don't do anything in this example, I created this in MATLAB, so this is a very simple system. So in this example, I get this response. I call it the unmanipulated response. Of course, it has a large overshoot over here and a long settling time. The idea, what we want to do is we want to kind of get a response with a smaller overshoot and response that settles faster. So what we do is we are, instead of keeping this set point at x2, when we are noticing that the response is going to have an overshoot, what we do is we're going to move that set point around. As you can see over here, we are going to reduce that set point by a certain factor. And once I do this, now my system tries to track this new set point. So it's going to slow down, as you see in this black trace. And then when it has slowed down sufficiently, then I'm going to release the set point back. So it goes to X2, and then I'm getting this nicer response. Essentially, my overshoot is very, very small. Settling time is a fraction of what I had before. So this is the essence of the idea. Extremely simple, also very effective. We're going to see a number of case studies to see how this method works. But first, so in terms of how this method is going to be implemented, so you have this standard control methods, a unit, your inverter, the primary controller, and typically these two are in a gray box because that comes as part of the inverter. And at the set point that comes from some higher level control. What we are doing here is we are adding this set point modulation block that looks at the set point, looks at the response of the system, and based on these, it's going to manipulate the set point that actually is fed to the inverter system. And we are hoping that we get a response as beautiful as what I'm getting over here. So in a sense, what we are doing is we are actually closing another loop around the existing control loops of the system. So we are adding this loop. All right. So of course the question is, how do I do this? Now we have shown for certain systems, and again a disclaimer. I'm talking about this to kind of have some confidence, to give you some confidence that this method is implementable. The idea does work. We are going to talk about the actual implementation in a bit, but let's see actually this method does work. So our initial idea was to apply this change, this modification in the set point at some point T1, and then release that set point at some point T2, and then if you look at the response of if you essentially play long enough with the response of the system, you see that one of the good things you can do here is if you choose this time T1, so that it's when I reduce this, the peak of this response, this value over here, equals the reference, and that's how we choose my T1. And then T2, the time that I release the set point, would be the time of this peak. So in this case, I actually need to release the set point exactly at this point. So here's an example. This is the original response. This is now when I apply a set point change at time T1 and I release it at T2. Now this T2, you see that it's not exactly time of peak. Interestingly, my response is already better, but I was hoping for something even nicer than this. So let's see what happens when T2, which is this time, becomes closer to time of the peak. So that's my next attempt. Response is better now. T2 becomes closer to time of peak. Better response, even better now. And this is exactly when T peak and T2 coincide. They're the same value. So in this case, you see that I have no overshoot. I have no essentially delay in getting the response settled. A very beautiful response, right? I mean, if I can have this, then I can essentially finish my job and go home. The problem is it's not really implementable this way, right? So the idea does work if I knew what T1 and T2 were, but the problem is that's actually too much to ask. To know T1 and T2, you either have to have a fancy, faster than real-time simulator, or you have to have the closed form solution of the system. Somehow you need to be able to predict that the behavior of your system. Of course, system parameters is needed too, which is, again, something that we don't necessarily have. We're not going to get too disappointed. It's true that we cannot implement this method based on T1 and T2 calculations, but there are still ways to implement this, because otherwise I wouldn't be talking about this approach here. So in fact, there are multiple ways. I'm going to walk us through those methods. So again, we have a good theoretical solution, but we're going to see how we can actually implement that. But it's a good start. I mean, we know that we are onto something. Our first iteration was actually to implement this idea based on a finite state machine, which essentially looks at the violations of the limits, looks at the changes in the response of the system, and based on those manipulates the set point. This is an earlier version of our finite state machine. I'm not actually going to go through the details of this for two reasons. First, of course, it can get complicated. As I said, this is only the simpler one. We have the first iterations. At the same time, as I mentioned, we have even better ways of implementing this approach, which we, by the way, call SPAACE, short for set point automatic adjustment with correction enabled. This implies that there was actually an earlier version of this without this correction, but we're not going to talk about that. So before I move on to showing kind of our case studies based to show kind of how we improve this method, I'm going to show some of the earlier case studies we implemented using this finite state machine, and see how our our method actually works, and then we are going to improve that. So the first case study, we are using the IEEE 34 bus system. We added 3 DG units, one here, one here, one here. And this one operates in the grid connected mode. I'm going to apply a set point change in DG2 in the current. The top figure shows the response when SPAACE is not active. So I have about 40% overshoot and a longer settling time. Here's the response that I get when a SPAACE is active. You see SPAACE has applied these temporary changes in the set point, and then as a result, I get a response that is much better than the original response. I'm saying much better because those transients, this 40% overshoot that I'm experiencing here, could actually violate the limits of the switches that I have in that the inverter system. So I do not want to have those. So in one simulation scenario, you're saying that this method is working. So let's look at another scenario. One of the beauties of this approach is that it can be effective even when the disturbance in the system is not necessarily a result of a set point change. We just mentioned microgrids have to be able to operate in grid connected mode and islanded modes. So that transition is going to introduce some disturbances. Connection of new sources or disconnection of loads, those are going to also introduce disturbances in our system. Here we are looking at a load disconnection scenario. So again, same system as before. I have this load over here and I disconnected. Of course, when I disconnected, my system is going to go through some transients. Here is the current response. I have about 15% overshoot, the black trace we're looking at. And when the SPAACE is active, I still obviously have some transients, but I do not violate the limits. In this case, I had 10% over the 1 per unit value. So I do not violate the limits. So we are seeing that the SPAACE does work in this scenario as well. Let's look at another scenario, essentially looking at the robustness of our approach. We are looking specifically at an unbalanced system. So the 13 bus system, which is an unbalanced feeder, and we added a DG unit, a test load, and this is not going to operate in the islanded mode. So it's going to be also be kind of harsher compared to the previous case. Previous case, we were looking at current control. Now here we are looking at voltage control. So what happens here is I'm going to disconnect this load and see what happens. So without a SPAACE, I see this black dashed trace. As you can see, I have a fairly sustained oscillatory behavior of voltage. I enable SPAACE, and then I get this yellow trace, which essentially is able to settle the voltage in about 1 second. So significant improvement. Essentially, we are turning an oscillatory response into a stable response in this case study. So, so now let's take the idea one step further and look at a variant of SPAACE, which we call smooth SPAACE. So why? Remember, we said the original version, we were implementing that using a finite state machine. and we were applying set point changes that were kind of like a step like this, right? So we're going to address those. First, there can be scenarios when I use a state machine, my kind of my machine can get stuck in one certain state. In that case, SPAACE would try to apply multiple changes in a set point, only to find that they're not going to do much, and then we won't see much improvement. The way that we implemented the state machine in even the previous work was actually it would detect those kind of repetitive kind of changes in the set point, and then at some point it would not apply further changes in the fear that it would make the system unstable. So, but it's good to actually not have this problem. So that is one reason that we are looking at kind of a better implementation. And then the other reason is the type of set point changes we apply using the SPAACE are step changes. And in several applications, probably the more kind of dominant example is drives. You do not actually want to apply step changes in a set point because that could cause too much stress. In fact, too much mechanical stress. In fact, many drives applications do not apply a set point directly to the system either. They apply it through a low pass filter. So kind of a benign change in set point, very slow. Of course, the drawback is it's going to make your system, your controller slow. So we're going to how we can approach this problem with an improved solution now. So the first kind of iteration, the first idea that we had was essentially to make sure that set point changes were smooth. So instead of applying a set point change in a step form, we're going to make it proportional to the predicted tracking error. So my set point, it remains the same. I'm not modifying the set point if the error is small, essentially limited within my bounds. And then I would change it with a factor m of t, which is essentially some scaling factor m times predicted error. So if the predicted tracking error is big, I'm going to apply a larger change in the set point to kind of compensate for that error. And if it's small, then I'm going to also make the modification smaller. Here we are using a predicted kind of a form of the error to speed up the process. What I'm showing here is a date lag kind of predictor. We can use other approaches as well. So most of the examples that I'm going to be showing, most of them are going to be using a linear predictor. And then another thing is, in the first iteration, we said we apply a change in set point only if the error is outside the bounds. It turns out actually we do not need to check for that. You can just remove the conditional statement and apply this term as the modified set point all the time. Of course, if the error is small, then the modification would also be small as well. So this makes the implementation of this approach very, very simple. Makes also stability analysis and essentially looking at the theoretical behavior of the method also simpler as well. So let's see how now my my controllers would work with this updated implementation. So I'm going to show some of the experimental results because, of course, we always wondered, okay, well, what I do in PSCAD simulations, it's beautiful and nice, but how do I know that it actually would, I would be able to get similar results in real world? So there are two sets of the experiments here, some based on a drive system, which we actually work with the TU Graz and Austria in essentially an inverter-based load, which was the drive. I have a DC machine that would be in the back. It's not very obviously, very clearly seen here, but this is essentially the DC motor, and as a load, it uses an induction. Sorry, the DC generator, and as a load, it uses an induction motor. The controller is implemented in DSpace, which essentially uses a variant of Simulink. So we implemented this, and DSpace. It's uploaded to the controller, and then we're looking at certain scenarios. The first case, you're looking at step change in the speed set point. On the right, I'm showing simulation results, and on the left, I'm showing the experimental results. If you look closely, actually, these results are very, very, very similar. So I'm going to focus on experimental results now. And we're looking at 4 different types of controller implementation. A is the base controller. I'm not doing anything. Essentially, that set point change is applied directly to, to the machine. Case B is a pre-filter. As I mentioned, for drives, we actually apply the set point change through a low-pass filter. So we are not subjecting our system to our changes. And then case C is our original space when we apply this set point changes as a step. And then case D is what we are really showcasing here is the smooth variant of space, where we are looking at the updated implementation of the space. So as I said, we apply a set point change from 5 in speed from 500 RPM to 600. The black trace in each case shows the adjusted set point. So of course, in the base case, there is no adjustment. When I have the low pass filter, of course, my set point goes to, essentially becomes smoother. And this is the space and SS space modified set points. Without any additional measure, my response has 40% overshoot, that is case A, and 140 milliseconds of settling time. Now, the pre-filter approach, of course, it makes the overshoot smaller, but I still have some oscillations, and then the system becomes slower because of the nature of that filter. With the space, I get a faster rise time. Again, I still have some oscillations. The real improvement comes with our newest implementation, SPAACE, that we get an overdamped response with practically no overshoot. So let's look at actually the numbers. This is the same slide, the same kind of case study, except that now I have superimposed all the responses on top of each other. So I have the base case, pre-filter, space, and SSpace. So with just naked eyes, it's quite obvious that the black trace, which represents the response with SSpace, has really good behavior. If you look at the numbers, the base case has 42% overshoot and a settling time of 140 milliseconds. SSpace has a very small overshoot, 4%, with a settling time that is about 1/3 of what I had before. Rise time has stayed the same. This is kind of different from the pre-filter case, that it does reduce the overshoot, only 10%, but it also increases the rise time. So with SSpace, I get the best of both worlds. Overshoot is a small, settling time is a small, and rise time has not really changed, essentially because of the way that the space works, it's not going to really apply any changes in the set point unless it feels that we are going to violate the limits. And at this point, essentially 67% of the step space is not really active yet. That's why we are not going to see much difference between the base case and the SSpace case. So another case, this is load change, where the disturbance in the system is not because of a set point change. And you're seeing that essentially pre-filter is hopeless because pre-filter works on the set point. There is no set point change, so pre-filter is not going to do much for us. The deviations in speed that I get when I have a load change, with the base case, I have 48 RPM change. That's about 50%, sorry, 10% overshoot or undershoot. Pre-filter is the same. With space, I get only 12 RPM. So again, you can see that the response that I'm getting over here is much better than the response that I was getting with the other methods. And we also were interested to look at the sensitivity of this approach to the system parameters. What we did in this particular case study was to change the inertia constant of the system. Of course, we didn't do this in experiments. We did it only in simulation because it's you can change the inertia of a motor quite easily. So once we are changing, you're looking at the inertia that is 1/3 of the original inertia. And then another case when you're looking at the case where the inertia is 3 times as much. So again, we're changing the speed from 500 to 600 RPM and then back to 500. The base case has an overshoot of 50% and a settling time of 80. With SPAACE, again, the red trace is what you are looking at over here. My overshoot is practically 0%, and settling time is 50%, so shorter than the original 80 milliseconds. This is actually some really encouraging results, because remember we were talking about losing inertia and low inertia grids. So in this case, we're showing that if we have good controls, that won't really have impact on our system kind of controls with the space. Of course, there is more to a power system than just the primary controls, but at least this shows that with our implementation, a reduction in the inertia is not going to really cause issues for our control system. And then the other case, having a bigger inertia, obviously the system is going to become slower. So instead of the 80 milliseconds in original response, I'm getting 400 milliseconds. But even here, SPAACE or SPAACE is reducing the overshoot. So from 40%, I'm going down to 10. And from 400 milliseconds, I'm going down to half of that, 0.2 seconds or 200 milliseconds. So, so again, looking at very encouraging, very promising results here. And then another study system is, so the previous one was when our load was inverter-based. Here we are looking at a generation that is inverter-based. So this is on based on collaboration we had with the University of Strathclyde in the UK. So essentially there's a microgrid testbed, and quite a few years ago, and then with inverters, batteries, and mechanical loads, and so on. So we are going to look at some quick case studies here as well. This is actually a very efficient slide. We are looking at 7 different scenarios in kind of type of disturbances that are introduced in the system. Real power change, voltage change, virtual impedance change. That was essentially the control method that was implemented for the DRs, and induction motor energization. So you're looking at these scenarios. The kind of this bar chart shows the tracking error, essentially kind of the integral between the set point and the actual response. The blue trace shows the base case, so I have actually the highest tracking error in that case. The red, there are several cases. This red one is actually when I use SPAACE with the linear prediction. The other ones are different types of prediction approaches. We didn't really talk about them, but that can also have an impact on the performance. You see that most of the time, in terms of simplicity and the performance, a simple linear predictor is giving us very, very good results. And then on the left, we are looking at the actual response of the system for different prediction scenarios. Let's just focus on the linear one. So the red trace shows the response with the SPAACE, and the blue trace shows the original response. Again, just looking at this, you can see that the SPAACE has been able to reduce the transients, essentially getting a much better response, fewer oscillations, faster settling time, and some of the oscillations that we saw in the original response don't really exist with the SPAACE. For example, cases 4 and 5, which is the virtual impedance changes. So essentially, we don't have much variations with the SPAACE. Let me skip this. And then let's just take a step back and talk about why does this method actually works, right? So why is the reason that this method seems to be successful? So as we said, we are adding a second control loop around the original control loop of the system. So this is what I had, and then I'm adding this set point modulation block around that. So, and if you remember, the reason we did this was because we didn't have access to this primary controller, but instead we wanted to improve the response of the system. So we said we would do it with this external control loop. Now, in case of SPAACE, effectively what we are doing is we are adding a predictive term to our control system. So I'm not showing the equations over here, but if you do write the equations, even for, say, a PI controller with some arbitrary transfer function for the rest of the system, you see that the effect of adding this extra control loop is, for example, if you're using a PI controller, it really adds a D term, kind of a differential term, and kind of changes your PI into a PID. And because of that, it improves your performance. And then even if I do not use a predictor, so we mentioned we use prediction to improve the performance, but even if I do not use a predictor, still this act of kind of set point modulation still improves the response, because it boils down to really boosting the P term that I have in the, say, assuming the original control is PI, it effectively boosts that P term, so makes the system, the proportional term, so it makes the system faster. So it's not all magic. There's a reason behind it. I have, I think, 2 or 3 slides. I'm not going to go through these in much detail. Just in case you are interested in more kind of a mathematical treatment of this approach. For example, why and how do we know actually a better response does exist? So we have worked on essentially kind of some derivations, and essentially you can show that there are times T1. So for our simpler implementation, there are times T1 and T2 that if you do apply the set point change, then you get this improved performance. The proof is quite simple. We're using the intermediate value theorem, which essentially says if your function is negative at some point and positive at some point, some other point, it's gotta have it's gotta cross 0 at least one point. So the proof really boils down to defining an appropriate F and defining appropriate T1s and T2s. And based on that, we show that there exists actually this time T1 that gives us this performance. We actually can use the same kind of augment this approach to find an upper bound for M. M is the scaling factor that we use, essentially how much we are going to change our set point. And then the effect on stability, essentially the idea is the space does not make an unstable system. It does not make a stable system unstable. And as we saw in some of our case studies, it may make an unstable system stable. So with that, let me stop here. This is a number of papers that we have written based on this work. And I think I would stop here. If there are any questions, I would be happy to answer those.